Welcome to Science Nap, where we kick back, let curiosity sprawl out on the couch, and watch science meander its way toward dreamland. Tonight, we're unraveling time. Yep, that weird, slippery thing we're all stuck with, but can't really wrap our heads around. What is time, really? The question that haunts us. Have you ever stared at a clock and felt a strange sense of disbelief? That relentless, rhythmic tick, tick, tick. It's the soundtrack to our lives. It tells us when to wake up, when to work, when to sleep. It measures our birthdays, our anniversaries, our deadlines. But have you ever truly stopped and asked yourself the question that has haunted philosophers, poets, and physicists for millennia? What is time, really? Is it a real, fundamental force of the universe, like gravity? A river flowing in one direction, carrying everything in its current? Or is it something else entirely? What if it's just an illusion, a story our brains tell us to make sense of a chaotic universe, a complex trick of memory and perception? What if I told you that for a lonely astronaut speeding through the cosmos, only a few years might pass, while back here on Earth, centuries would turn to dust? What if I told you that at the edge of a black hole, the single most terrifying and mysterious object in the universe, time itself, grinds to a halt? An eternity could pass for the rest of us, in the blink of an eye for someone hovering at that precipice. For thousands of years, we've tried to capture time, to measure it, to master it. We built sundials and water clocks, atomic clocks and digital calendars. We've written poems about its fleeting nature and symphonies about its grand, sweeping march. From the ancient sages of India, who imagined time as a great, repeating wheel, to Albert Einstein, who shattered our common sense with a single equation, we have been on a relentless quest to solve this ultimate puzzle. So, this is your invitation, an invitation to journey with us. We're going to travel back to the dawn of human consciousness. We'll stand on the shoulders of giants who redefined reality. We will dive into the bizarre world of quantum mechanics, and we will get lost in the mind-bending paradoxes that twist logic into knots. This isn't just a story about physics. It's a story about us, about our perception, our mortality, and our place in the cosmos. So, pour yourself a drink, get comfortable, and prepare to question everything you thought you knew about the past, the present, and the future. Because the answer to what is time might be more strange, more beautiful, and more terrifying than you could ever imagine. Our journey begins now. The rhythm of the ancients. Long before the digital glow of a smartphone, long before the precision of a Swiss watch, humanity's first clock was the universe itself. It was immense, reliable, and hung right above our heads. For our earliest ancestors, time wasn't a number. It was a rhythm, a feeling. It was a story told by the sun, the moon, and the stars. The rising sun was a promise. It meant the cold and dangers of the night were over. It was time to hunt, to gather, to build. The day was a cycle of light and warmth. The setting sun was a warning, a call to return to the safety of the fire, to share stories, to rest. The shadow of a mountain or a tall rock became a natural clock, its creeping movement across the valley floor marking the slow death of the day. But the sun was just one hand on this cosmic clock. The other was the moon. Imagine a Cro-Magnon artist, 30,000 years ago, living in what we now call France. They didn't have a calendar app, but they had the moon. They watched it wax from a sliver to a brilliant full orb, and then wane back to nothing. On the walls of their caves, or on pieces of bone, they etched marks, dots and lines, arranged in a serpentine pattern. Archaeologists now believe these weren't just decorations. They were lunar calendars, the first human attempt to record the passage of longer stretches of time. to predict the cycles of nature, to count the days between one full moon and the next. This wasn't just abstract record-keeping, it was a matter of life and death. Knowing these cycles meant knowing when herds of bison would migrate, when salmon would run up the rivers, when certain plants would be ripe for harvest. To understand time was to understand how to survive. As human societies grew more complex, so did their methods of measurement. In ancient Egypt, the civilization that rose from the banks of the Nile, time was everything. The river itself was a clock. Its annual flood, predictable and life-giving, dictated the entire rhythm of their society, a time for planting, a time for growing, and a time for harvesting. To measure the hours of the day, they erected massive stone pillars called obelisks. These were the world's first public clocks. As the sun moved across the sky, the obelisk's shadow would sweep across a set of markers on the ground, telling the priests and the public the hour. It was a simple genius-level technology, a monumental sundial. But sundials had a fatal flaw. They didn't work at night or on cloudy days. The Egyptians and many other cultures,
these weren't just for show. They were used in temples for nightly rituals and in courts of law to time the speeches of lawyers. For the first time, humanity could measure time in the dark. Time was being tamed, brought indoors, separated from the direct movements of the heavens. Across the world, civilizations were solving the same problem with their own unique ingenuity. In ancient China, during the Song dynasty, an astronomical genius named Su Song built a colossal, intricate water-powered clock tower. It was over 40 feet tall, a mechanical marvel of chains, wheels, and levers, all driven by a giant water-turning wheel. It didn't just tell the time, it tracked the sun, moon, and planets, with wooden puppets that would emerge from doors to ring bells and bang gongs, announcing the hour. It was the ancestor of all mechanical clocks. In ancient India, the Gati yantra was used. It was a small copper bowl with a hole in it, placed in a larger basin of water. It was designed to fill with water and sink after a precise, repeatable amount of time, often 24 minutes, a unit of time called a gatika. When it sank, it would often strike a gong, marking the passage of time for the entire village. From the intricate calendar systems of the Maya in Central America, who tracked vast cosmic cycles lasting thousands of years, to the Greek philosophers who began to debate the very nature of time itself, a universal pattern emerges. Humans have an innate, desperate need to measure the world around them. But as they measured time, they also noticed something strange, something personal. Time didn't feel the same for everyone, or even for the same person in different situations. Imagine that ancient farmer, his fields dry and cracked, praying for rain. For him, a single week of waiting could feel like a lifetime. Each sunrise was a disappointment. Time was a slow, agonizing crawl. Now imagine a young hunter, heart pounding, adrenaline coursing through her veins as she tracks a deer through a dense forest. The sun can arc from morning to afternoon in what feels like a blink. Time is compressed, urgent, almost non-existent. This is the great duality of time. We can measure it with astonishing precision, yet our experience of it is completely subjective. It's a personal, emotional, psychological phenomenon. When you're bored in a Monday morning meeting, a minute can stretch into an eternity. When you're laughing with your closest friends on a Saturday night, hours can vanish in a flash. The ancient world understood this in a way we've perhaps forgotten. Time wasn't just a series of numbers on a device. It was a feeling, a rhythm. It was the heartbeat of the world, connected to the seasons, the tides, the cycles of life, growth, decay, and death. Some cultures, in Hindu philosophy, the concept of Kala Chakra, the wheel of time, dominates. The universe isn't on a one-way trip. It's in a perpetual cycle of creation, existence, destruction, and rebirth. A cycle that lasts for trillions of years before starting all over again. In this view, there is no final end, only another beginning. The Greek philosopher Heraclitus stood by a river and came to a profound realization. He said, "You cannot step into the same river twice." He meant that the river is in constant flux, the water is always new. So too is the universe. Everything is in a state of perpetual change. Time, for Heraclitus, was this flow, this constant becoming. And yet, despite this deep, intuitive understanding of time as a flow, a cycle, a feeling, we humans kept pushing. We wanted more precision, more control. We wanted to chop time into smaller and smaller pieces, to make it predictable, to make it the same for everyone, everywhere. We were building a world based on a shared, universal clock. Little did we know the universe had a secret. A joke, almost. The secret was that a universal clock doesn't exist. Centuries later, a humble patent clerk in Switzerland would publish a paper that would tear down this entire worldview. His name was Albert Einstein, and he was about to tell the world that the most constant thing in our lives is not constant at all. But before we take that leap into the dizzying world of modern physics, we need to understand the machine that creates our own personal experience of time. The most complex clock in the known universe, our brain. In the next chapter, we'll discover how this 3-pound lump of tissue constructs our past, present, and future, and why that feeling of time flowing might just be the most powerful and most convincing illusion of all. The Clockwork God and the Rebel Clerk. For centuries after the fall of Rome, the deep philosophical questions of time took a back seat to a more practical concern: building better clocks. The water clocks of the ancients were good, but they weren't perfect. Water could freeze in the winter or evaporate in the summer. They required constant refilling. Humanity needed a new engine for timekeeping. And in the 13th century, in the towers of European cathedrals, it arrived. The mechanical clock. These were gargantuan, iron beasts. They didn't have a face or hands. Their job was simply to ring a bell, a clocka in medieval Latin, to call the monks to prayer. They were driven not by water, but by the slow, steady pull of gravity on heavy weights. But the key invention, the breakthrough that made it all possible, was something called the escapement. It's a device that stops and releases the clock's gear train at a regular interval, producing that characteristic tick-tock sound. It chopped the smooth flow of gravity into discrete, measurable, identical beats. For the first time, time was being quantized. It was being turned into digital information. Tick-tock, 1 second, the next second. This invention changed the world. Clocks spread from church towers to town squares. They synchronized labor, commerce, and social life. The rhythm of the sun was being replaced by the rhythm of the machine. The idea of being on time was born. This mechanical precision reached its zenith with one of the greatest minds in history, Sir Isaac Newton. Newton, in his masterwork, the Principia Mathematica, laid out the laws of motion and universal gravitation. To make his physics work, he needed a stage for the universe to play out on. That stage was made of absolute space and absolute time. For Newton, Time was a divine, invisible entity. He called it absolute, true, and mathematical time. It flowed equably, without relation to anything external. What did that mean? It meant that time was a cosmic river, flowing at the exact same rate for everyone, and for everything, everywhere in the universe. A second on Earth was the exact same length as a second on Jupiter, or in a distant galaxy. Time was the ultimate, incorruptible deity. It was the master clock of God, and we were all just living by its unchangeable tick. This idea was powerful. It was intuitive. It confirmed everyone's daily experience. It became the bedrock of science for over 200 years. The universe was a giant, predictable clockwork machine, wound up by God, and ticking along according to Newton's perfect laws. Case closed, right? But the universe is sneakier than that, and at the turn of the 20th century, cracks began to appear in Newton's perfect clockwork reality. Scientists were experimenting with electricity, magnetism, and the speed of light, and the results just weren't adding up. They were getting weird. And in Bern, Switzerland, a 26-year-old patent clerk was thinking about these weird results in his spare time. He wasn't a famous professor at a grand university. He was a man who, as a student, had been told he was lazy and wouldn't amount to much. His name was Albert Einstein. Einstein was obsessed with a simple question that he'd been asking himself since he was a teenager. What would you see if you could ride alongside a beam of light? According to the physics of his day, light was a wave. So, if you could match its speed, you should see a frozen, stationary wave of light next to you. But this was impossible, according to the equations of electromagnetism. Light speed, c, was supposed to be a constant, no matter how fast you were moving. This paradox tormented Einstein. For something to be true for everyone, no matter their motion, something else had to give. Something we thought was fundamental. Something we took for granted. In 1905, in what historians call his miracle year, Einstein published a paper on his special theory of relativity. In it, he proposed a breathtakingly radical idea. He said the speed of light is indeed the one true constant of the universe. To make that possible, space and time themselves must be flexible, malleable, relative. This is where your brain might start to hurt, and that's a good thing. Einstein said that the faster you move through space, the slower you move through time. Let that sink in. Imagine two twins, Anna and Ben. Anna stays on Earth. Ben gets in a futuristic spaceship and travels to a nearby star at, say, 99% of the speed of light. From Ben's perspective inside the ship, everything is normal. His heart beats at a normal rate. His clock ticks 1 second at a time. To him, the journey takes maybe 5 years, but because he is moving so incredibly fast relative to Earth, time for him is passing much, much slower than it is for Anna. When he finally turns around and comes back to Earth, he will have aged only 10 years, but on Earth, 70 years will have passed. His twin sister, Anna, will be an old woman. His friends will be gone. The world he knew will have changed beyond recognition. This isn't science fiction. It's called time dilation. It is a proven, measured, physical reality. Scientists have confirmed it. They've placed ultra-precise atomic clocks on jumbo jets and flown them around the world. When the planes landed, the clocks on board were a few nanoseconds behind the clocks that had stayed on the ground. The pilots were, quite literally, a tiny fraction of a second younger than they would have been if they had stayed home. The GPS in your phone, the one you use to order a pizza or find the nearest coffee shop, has to account for this effect. The GPS satellites are moving very fast in orbit, so their internal clocks tick slightly slower than ours on the ground. If the engineers didn't correct for Einstein's time dilation, your GPS would be off by several miles every single day. Newton's absolute universal clock was dead. Einstein had killed it. Time wasn't a rigid divine river, it was a personal, shifty, stretchy thing. There is no universal now. My now could be your past if we are moving fast enough relative to each other. But Einstein wasn't done. For 10 more years, he wrestled with an even bigger problem: gravity. His special relativity only worked for constant, steady motion. What happened when you accelerated, or when you were in a gravitational field? The answer, when it came to him, was what he called the happiest thought of his life. He realized that gravity wasn't a force pulling you down, as Newton had said. Gravity is the shape of the universe itself. He said that space and time are not separate things. They are woven together into a single four-dimensional fabric, space-time. Think of it like a giant cosmic trampoline. If space-time is empty, the trampoline is flat. But if you place a heavy object on it, like a bowling ball representing the sun, the fabric curves and dips. That curve is what we feel as gravity. The Earth isn't being pulled by the sun, it's just following the straightest possible path through the curved space-time created by the sun's mass. And here is the final mind-shattering piece of the puzzle. It's not just space that gets warped by mass and gravity. Time does too. The stronger the gravity, the more space-time is curved, and the slower time flows. This means that time on the top floor of a skyscraper literally passes a tiny bit faster than time on the ground floor, because the ground floor is slightly closer to the Earth's center of gravity. This too has been measured with hyper-accurate clocks. You age faster living in a penthouse than in a basement. But this effect becomes truly extreme when you deal with objects of unimaginable mass and density. Objects where gravity has become so powerful it has crushed space and time into a singularity, objects we call black holes. And at the edge of one of those, the rules of reality and the flow of time as we know it come to a terrifying end. That's where we're going next. At the edge of forever, there are monsters in the universe, not monsters of flesh and fang, but of physics, monsters born from the corpses of giant stars. They are points of infinite density and zero volume, wrapped in a cloak of pure darkness. They are black holes. A black hole is what happens when matter is crushed beyond all known limits. It's a place where gravity is so overwhelmingly powerful that nothing, not even light, the fastest thing in the universe, can escape its grasp. The edge of this abyss, the point of no return, is called the event horizon. The edge of this abyss, the point of no return, is called the event horizon. The event horizon isn't a physical surface. You could fly right through it without feeling a thing. It's a one-way door in space-time. Once you cross it, all paths, all possible futures, lead to only one place, the crushing oblivion of the singularity at the center. But we're not here to talk about what's inside. We're here to talk about what happens near it. Because this is where Einstein's strange ideas about time go from being a subtle curiosity to a reality-shattering spectacle. Let's go on another thought experiment, but this one is more perilous. Imagine two explorers, Maya and David, in two identical spaceships. They travel to Gargantua, a supermassive black hole. David decides to stay in a safe, stable orbit, far from the event horizon. Maya, the braver of the two, is going to get closer. She will carefully pilot her ship to hover just outside the point of no return, using her powerful engines to fight the immense gravitational pull. From David's perspective, watching through his telescope, something bizarre begins to happen as Maya's ship gets closer and closer to the edge. Her ship seems to slow down. The light from her engines appears to shift towards the red end of the spectrum, a phenomenon called gravitational redshift. And most strangely of all, her movements inside the cockpit, if he could see them, would appear to be happening in extreme slow motion. Why? because she has descended deep into the black hole's gravity well. Space-time around her ship is warped like a waterfall, and just as water speeds up as it goes over the edge, time for her is slowing down dramatically relative to David. Let's say David watches Maya for 1 hour on his clock. He calls her on the radio. Maya, it's been an hour. How are things? For Maya, in her own frame of reference, time is flowing perfectly normally. Her heart beats once per second. Her thoughts are clear. But when she looks at her clock, she sees that only 1 minute has passed. She radios back. David, what are you talking about? I've only been here for 60 seconds. This is extreme gravitational time dilation, and the closer Maya gets to the event horizon, the more extreme the effect becomes. If she could get perilously close, to the very razor's edge of safety, a single hour for her could be equivalent to a decade for David, or a century, or 1,000 years. The rest of the universe would be racing by and fast forward. From her vantage point, she could watch stars be born and die in the blink of an eye. She could see entire civilizations rise and fall on distant planets. She would become a godlike observer of cosmic history. Now for the truly terrifying part. What would David see if Maya's engines failed, and she fell past the event horizon? He would never see her cross it. As she fell closer, the time dilation would become infinite. From his point of view, her ship would appear to slow down more and more, getting dimmer and redder, until it seemed to freeze in place, pasted onto the event horizon for all eternity, like a fly caught in amber. Her final moment stretched out forever. But for Maya, her fate would be swift and violent. She would cross the event horizon without any fanfare. But once inside, the tidal forces of gravity, what scientists grimly call spaghettification, would take hold. The gravity at her feet would be so much stronger than the gravity at her head that her body would be stretched and pulled apart, atom by atom, into a thin stream of plasma. A brutal but quick end. So, time, which felt so reliable back on Earth, becomes a deadly variable in the presence of extreme gravity. It's a dimension that can be stretched, twisted, and brought to a near standstill. Einstein's theories revealed a universe far stranger than Newton's clockwork model. It's a dynamic, rubbery reality where our neat little measurements are just local approximations. But this raises a profound question. If time can be so radically different depending on where you are and how you're moving, what about the clock we all carry with us? The one that makes time feel fast or slow, even when we're standing perfectly still. The problem of time isn't just out there in the cosmos, it's right here, between our ears. We've explored the universe's clock. Now it's time to explore the clock inside our head. The clock inside your head. You're driving down the highway. The sun is out, your favorite song is on the radio, and you're in the flow. An hour passes, but it feels like 15 minutes. Now, you're in the dentist's chair. The sound of the drill whirs in your ear. You're tense, you're uncomfortable. 5 minutes feels like an hour. Same universe, same laws of physics. Time on the atomic clocks at the National Observatory is ticking along just fine. So what's going on? Why is your personal experience of time so flexible? The answer lies in the most complex and mysterious object in the known universe, your brain. For a long time, scientists searched for a single centralized clock in the brain, a specific region like a tiny grandfather clock in your head that was responsible for timekeeping. They looked at the suprachiasmatic nucleus, a part of the hypothalamus that governs our 24-hour circadian rhythms, our sleep-wake cycles. And while that's a crucial biological clock, it doesn't explain our moment-to-moment perception of time's passage. The modern view is far more complex and fascinating. It seems our brain doesn't have one clock. It has many clocks, all working at once. And our sense of time isn't a direct perception of reality. It's a construction, a story the brain tells itself, based on information, memory, and emotion.
One of the key players in this story is a neurotransmitter you've probably heard of: dopamine. Dopamine is often called the pleasure molecule,
but it's more accurately the motivation molecule. It's involved in reward, focus, and anticipation, and it seems to directly affect our internal sense of speed. Think of it like this. Your brain has an internal pacemaker, a steady beat of neural pulses. When you're engaged, excited, or having fun, your brain is flooded with dopamine. This seems to speed up your internal pacemaker. Tick, 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 tick. Because your internal clock is ticking faster, it accumulates more ticks in a given period of external time. But when your brain looks back, it misinterprets this high number of ticks. It thinks, wow, that many ticks must have taken a long time. But because the external event was short, it concludes that time must have flown by. The opposite happens when you're bored or in a dull situation. Dopamine levels drop. Your internal clock slows down. Tick, tock, tick, tock. Fewer ticks are generated. When you look back at that period, your brain says, that was only a few ticks, so not much time passed. But because the external experience felt long and drawn out, you get that feeling of time dragging.
This explains why time seems to speed up as we get older. A child's world is full of novelty and new experiences. Everything is a first. The first day of school, the first bike ride, the first trip to the ocean. Their brains are constantly processing new information, creating rich, dense memories. This high cognitive load makes time feel expansive and slow. A summer vacation could feel like a lifetime. As an adult, life becomes more routine. The daily commute, the weekly meetings, the familiar chores. Our brains don't have to work as hard because they can run on autopilot. We form fewer new, distinct memories. A year can go by in a blur because there are fewer unique memory markers to anchor it in our minds. The timeline becomes compressed. But what about those moments of extreme fear or danger? People who have been in car accidents or life-threatening situations often report that time slowed down. They could see every detail, the shattering glass, the expression on someone's face, as if in slow motion. Did time actually slow down for them? No. Again, it's a trick of the brain. But this time, it's not about dopamine. It's about memory. In a high-stakes situation, a part of your brain called the amygdala goes into overdrive. The amygdala is your brain's threat detection center. It kicks your entire system into high alert and tells your memory centers, record everything. This is important. Your brain starts encoding memories with incredible richness and detail. It's laying down a much denser track of information than it normally would. Later, when you recall the event, you are playing back this incredibly high-fidelity recording. Because there's so much more data packed into those few seconds, your conscious mind interprets it as having taken longer to happen. The event feels stretched out in your memory. It's not that you experienced it in slow motion. It's that you remember it in slow motion. So our perception of time's passage is a fragile, subjective thing, easily warped by our neurochemistry and emotional state. But there's an even deeper illusion at play. The very idea of a flowing present, moving from a fixed past to an open future. This feeling is constructed primarily by memory. The past is simply the set of neural connections that represent events that have already been processed. The present is the thin slice of sensory information your brain is currently processing. And the future is your brain's projection. It's simulation of what might happen next based on past experiences. Without memory, you would be trapped in an eternal, meaningless present. You wouldn't know who you are, where you've been, or where you're going. You wouldn't have a story. You wouldn't have a self. This leads us to one of the most profound and unsettling ideas in all of science. We feel time flowing in one direction, forward,
always forward. You can remember yesterday, but you can't remember tomorrow. You can break an egg, but you can't unbreak it. Why? Why does time have a direction? The laws of physics from Newton to Einstein, even quantum mechanics, work just as well forwards as they do backwards. They are time-symmetric. So where does this one-way street of time, this arrow of time, come from? The answer isn't found in gravity or speed. It's found in chaos, disorder, and the single most fundamental law of the universe, the law of ever-increasing messiness. The arrow of time. Have you ever built a sandcastle on the beach? You spend hours carefully sculpting towers and walls. It's a structure of order and complexity. Then you walk away. The wind blows, the tide comes in, and what happens? The castle dissolves back into a smooth, featureless expanse of sand. Chaos reclaims order. Have you ever tried to do that in reverse? To stand on the beach and watch the waves and the wind spontaneously gather grains of sand and build a perfect castle? Of course not. It's ridiculously improbable. It never happens. This simple observation holds the key to one of the deepest mysteries in physics. Why does time have a direction? Why does it only seem to move forward? Scientists call this the arrow of time. As we saw, most of the mental laws of physics don't care about the direction of time. A video of two billiard balls colliding looks perfectly normal whether you play it forwards or backwards. A planet orbiting a star follows the same path, forwards or backwards in time. The equations work either way. So why is the macroscopic world, the world we live in, so different? You can't unstir the milk from your coffee. You can't unbreak a glass that has shattered on the floor. You remember the past, not the future. These processes are irreversible. The answer lies in a powerful and often misunderstood concept from thermodynamics: entropy. Entropy is, in simple terms, a measure of disorder, randomness, or messiness. And the second law of thermodynamics is one of the most robust and fundamental laws in all of science. It states that in any isolated system, entropy, or disorder, will always tend to increase over time. It's not a law that says things must get messier. It's a law of probability. It says that there are vastly, astronomically more ways for things to be disordered than for them to be ordered. Let's go back to that sandcastle. There is only one specific arrangement of sand grains that makes up your perfect castle. That's a low entropy, highly ordered state. But there are trillions upon trillions of possible arrangements of those same sand grains that just look like a flat, messy beach. That's a high entropy disordered state. So when the waves come, they aren't trying to destroy your castle. They are just randomly shuffling the sand grains. And because there are so many more ways to be messy than to be neat, the system will naturally, statistically, inevitably, move towards a state of higher messiness. This is the arrow of time. Time flows in the direction of increasing entropy. Think of an egg. A whole egg is a highly ordered system. The yolk is separate from the white, all contained within a shell. Low entropy. When you crack it and it splatters into a pan, it becomes a disordered mess. Yolk and white mixed together. High entropy. Could all those molecules of yolk and white spontaneously rearrange themselves, leap back up into the shell, and seal the crack? According to the laws of motion, it's technically possible. But the odds are so infinitesimally small that you would have to wait for trillions of times the age of the universe to see it happen. We see the past as the time when entropy was lower. We see the future as the time when entropy will be higher. Our memory itself works this way. Creating a memory requires energy and creates order in our brain. But in doing so, it releases heat and creates more total disorder in the universe around us, satisfying the second law. We remember the past because it was a state of lower entropy. This explains the arrow of time on a local scale. But it opens up an even bigger question. If the universe is always moving towards greater disorder, what does that imply about its beginning? It must mean that the universe began in a state of extraordinarily, absurdly, improbably low entropy, a state of perfect order. The Big Bang wasn't just an explosion of matter and energy, it was an unexplosion of entropy. The universe was born with its entropy wound all the way down, and the entire 13.8 billion-year history of the cosmos, the formation of galaxies, stars, planets, and life, is just the universe slowly, majestically, and irreversibly unwinding. It's just the sandcastle dissolving. The ultimate fate of the universe, according to this law, is a state of maximum entropy, a heat death, a cold, dark, empty void where everything is evenly spread out. No temperature differences exist, no work can be done, and nothing ever happens again. A final, permanent state of perfect, boring disorder. Time itself would lose all meaning. It's a grim thought, but it provides a powerful, physical reason for why our lives have a direction. Why we are born, we live, and we die. It's all just a small, temporary eddy of increasing complexity in a cosmic river flowing towards ultimate chaos. So we have time warped by gravity, bent by speed, constructed by our brains, and given its direction by entropy. It seems we're getting closer to an answer. But science has one more curveball to throw at us. A final descent into a realm so strange, so counterintuitive, that it makes black holes look tame. A world where time itself might not be fundamental at all. We must now journey to the smallest scales of reality, to the world of quantum mechanics. We've journeyed through the vastness of space-time and the intricate wiring of the human brain. But to truly grapple with the nature of time, we have to shrink. We have to go smaller. Smaller than a cell, smaller than an atom, down to the fundamental building blocks of reality itself. Welcome to the quantum realm. Down here, the familiar deterministic rules of Newton and even Einstein break down completely. This is a world of uncertainty, probability, and pure, unadulterated weirdness. Here, a particle like an electron doesn't have a definite position until you measure it. It exists in a superposition, a cloud of all possible locations at once. An atom can be in two places at the same time. Particles can become entangled, mysteriously linked across vast distances, so that measuring one instantly affects the other. This is the world described by quantum mechanics, the most successful and experimentally verified scientific theory in human history. It's the theory that gives us lasers, computers, and nuclear power, and it has a huge, glaring, and deeply troubling problem with time. Remember how Einstein wove space and time together into a single dynamic fabric called spacetime? Quantum mechanics handles the space part just fine, but the time part, it treats differently. In the standard equations of quantum mechanics, time is not a dynamic, flexible variable. It's treated more like Newton's clock, an absolute background parameter, a ticking clock against which the quantum weirdness unfolds. This creates a profound clash, a deep incompatibility between our two best theories of the universe. Einstein's general relativity, which describes the big and the heavy, and quantum mechanics, which describes the small and the light. This is the central challenge of modern theoretical physics, to find a theory of everything, a single framework of quantum gravity that can unite these two worlds. And at the heart of this challenge lies the question, what happens to time when you try to quantize gravity? One of the most famous attempts to write down an equation for the entire universe is called the Wheeler-DeWitt equation. When physicists John Wheeler and Bryce DeWitt formulated it, they discovered something shocking. The variable for time, the letter t, is completely absent from the equation. According to this leading candidate for a theory of quantum gravity, at the most fundamental level, the universe is static. It's timeless. There is no change, no flow, just a vast, frozen, probabilistic landscape of all possible nows existing at once. This is a mind-bending idea. It suggests that the flow of time, the thing that feels most real to us, is not fundamental. It's an emergent property. What does emergent mean? Think of temperature. A single molecule of water doesn't have a temperature. Temperature is an emergent property of the average motion of a huge collection of water molecules. It's a useful, real concept at our macroscopic level, but it doesn't exist at the fundamental level of a single molecule. In the same way, some physicists, like the controversial Julian Barbour, argue that time itself is an illusion. He proposes a timeless universe made up of an infinite number of distinct nows, which he calls configuration space. Each now is a complete, self-contained snapshot of the universe, a specific arrangement of all the particles and fields. So where does our experience of a flowing time come from? Barbour argues it's a trick of memory. Certain nows contain within them records or memories of other nows. Our brain, existing within one of these snapshots, sees these records and interprets them as a past, creating the illusion of a journey through a sequence of moments. Time doesn't flow. Our consciousness just connects the dots between these static cosmic photographs. This is a radical, fringe idea, but it highlights the deep crisis in our understanding of time. The arrow of time we talked about with entropy might also be part of this illusion. Our universe might be structured in such a way that the nows containing records of a past are simply more probable, more numerous than others. Another idea from quantum gravity is that space-time itself isn't smooth and continuous. At the tiniest possible scale, the Planck scale, it might be made of discrete, indivisible atoms of space-time. In this view, time doesn't flow smoothly. It jumps. It ticks forward in tiny quantized steps, each lasting for about 10 to the minus 44 seconds. This is the refresh rate of the universe. So incredibly fast that it appears perfectly smooth to us, just like the individual frames of a movie blend together to create the illusion of continuous motion. So, is time fundamental or emergent? Continuous or discrete? A real flow or a clever illusion? Science, for now, does not have the final answer. We are standing at the edge of our knowledge, peering into a darkness where our most basic intuitions fail us. We have journeyed from ancient sundials to the heart of a black hole, from the chemistry of our brains to the very fabric of quantum reality. We have gathered all the scientific clues. Now we must step back. We must ask not just what science says time is, but what it all means. What are the human philosophical implications of living in such a strange and slippery reality? It's time to enter the battlefield of ideas, where philosophers have been wrestling with the nature of our existence for centuries. For thousands of years, before Einstein and quantum mechanics, philosophers were already wrestling with the deep paradoxes of time. They didn't have particle accelerators or atomic clocks. They had something more powerful, pure reason. And the questions they asked still resonate today, perhaps more than ever. The central battle has always been about one thing: what is real? Think about it. Right now, this moment, the one you are experiencing as you hear these words, it feels real. This is the present. But what about the past? What about the moment you were born? It's not happening now. It's gone. It exists only as a memory in your mind and the minds of others, as a record on a birth certificate. But is the past itself real? And what about the future? The moment you will have dinner tonight, or your next birthday. It hasn't happened yet. It exists only as a possibility, a projection. Is the future real? This is the great philosophical debate between two opposing views: presentism and eternalism. Presentism is the common sense view. It's what most of us intuitively believe. It says that only the present moment is real. The past is no longer real, and the future is not yet real. Reality is just this thin, moving slice of now. The universe is constantly coming into being and vanishing, moment by moment. This feels right. It preserves our sense of free will. If the future isn't real yet, then our choices today can genuinely shape it. The future is open, a landscape of possibilities that we create with our actions. But presentism has a huge problem, especially after Einstein. If time is relative, and two people moving at different speeds can have different nows, then whose present is the real one? If my now can be in your past, how can we say that only one present moment is real? It seems to contradict the physics of relativity. This leads us to the other, more mind-bending view. Eternalism, also known as the block universe theory. Eternalism says that presentism is wrong. It claims that the past, the present, and the future are all equally real. The entire history of the universe, from the Big Bang to the final heat death, exists simultaneously as a single, unchanging four-dimensional block of space-time. Time doesn't flow, it just is. All the moments of your life, your first step, your high school graduation, this very moment, your 80th birthday, even your death, are all just different points in this block. They are all eternally there.
So why do we feel like time is flowing? The eternalist would say that our consciousness is just a spotlight moving along our personal timeline or world line within this block. We experience these pre-existing moments sequentially, giving us the powerful illusion of passage. This view fits perfectly with Einstein's relativity. It solves the problem of whose present is real. They all are, just at different coordinates in the block. But it comes at a terrifying cost: free will. If the future is already written, if it already exists just as solidly as the past, then are our choices real? Or are we just actors in a grand, cosmic play, reading lines that have already been scripted? Are we just experiencing the inevitable unfolding of a predetermined fate? This is a chilling thought. It turns our lives into a movie that has already been filmed. We are just watching it, frame by frame for the first time. So, which is it? Are we creators of an open future, or explorers of a fixed one? The ancient Greek philosopher Heraclitus, who said you can't step in the same river twice, was a kind of presentist. For him, the essence of reality was change, flow, and becoming. His rival, Parmenides, was an early eternalist. He argued that all change is an illusion. Reality is one, eternal, and unchanging. Our senses deceive us into thinking things come and go. This isn't just an abstract debate. It affects how we think about life, death, and regret. If presentism is true, then our mistakes in the past are truly gone. We can learn from them, but they no longer exist to haunt us. Our potential in the future is limitless. If eternalism is true, then our moments of joy are never truly lost. They exist forever in the block universe, eternally preserved. Your happiest day is still happening at its coordinate in space-time. But so are your worst moments. Your greatest regrets are also frozen there forever. Death isn't an end to existence, but simply the last point on your timeline within the block. So, what do you think? When you remember a happy memory, are you just accessing a neural pattern in your brain? Or are you, in some sense, looking back at a real place in space-time that still exists? The question of time forces us to confront the very nature of our reality. It's a puzzle where science and philosophy become inseparable. And this puzzle leads us to the ultimate what-if scenario, the one that has captivated human imagination more than any other. If time is a dimension, like space, can we travel through it? Can we break the rules? The time machine. It's one of the most powerful
and enduring ideas in all of fiction. From H.G. Wells to Back to the Future to Doctor Who. The fantasy of skipping through the ages, of visiting the past and witnessing the future, is an irresistible dream. But could it ever be more than a dream? Is time travel, according to the laws of physics, actually possible? The answer is a surprisingly definitive maybe. Traveling into the future is, in a way, surprisingly easy. We're all doing it right now, at a rate of 1 second per second. But if you want to speed things up, to take a shortcut, Einstein showed us how. As we saw, of time dilation, if you get in a spaceship and travel at near the speed of light, you can leapfrog into Earth's future. You could travel for 1 year on your clock and return to find a century has passed on Earth. So, one-way travel to the future is, in principle, physically possible. It just requires technology far beyond our current capabilities. But what about the real prize? The forbidden journey. Travel to the past. This is where things get truly tangled. Einstein's theory of general relativity does contain some bizarre solutions that could, theoretically, allow for travel to the past. These are called closed time-like curves. One hypothetical way to create such a curve is with a wormhole, also known as an Einstein-Rosen bridge. Think of spacetime as a sheet of paper. To get from point A to point B, you would normally have to travel across the surface. But a wormhole would be like folding the paper over and punching a hole through it, creating a shortcut through a higher dimension. If you could create a stable wormhole and then take one mouth of it on a round trip at near light speed, you could create a time machine. Stepping into one end and out the other could take you back to the moment before the wormhole mouth left. But even if this is mathematically possible, it's a practical nightmare. Wormholes, if they exist, are thought to be subatomically small and fantastically unstable, collapsing in an instant. Keeping one open would require a form of exotic matter with negative energy, something we don't know if exists or how to create. But let's say we could. Let's say you build a time machine. This is where the universe starts to throw paradoxes at you, puzzles that seem to have no logical solution. The most famous of all is the grandfather paradox. It goes like this. You travel back in time to when your grandfather was a young, single man, before he met your grandmother. In a clumsy accident, you cause him to have a fatal fall. He dies. Therefore, he never meets your grandmother. Your parent is never born. And if your parent is never born, you are never born.
But if you were never born, then who went back in time to kill your grandfather in the first place? The paradox creates a logical contradiction. The event happens, which causes it to not happen, which causes it to happen. It's a causality violation. Some physicists, like Stephen Hawking with his chronology protection conjecture, believe that the laws of physics themselves must have some unknown principle that forbids such paradoxes, making backward time travel impossible on a macroscopic scale. The universe, he argued, has a self-preservation instinct. But other solutions have been proposed. One is the Novikov self-consistency principle. This says that you can travel to the past, but you can't change it. Any action you take was already part of history. The universe is self-consistent. So, you go back to kill your grandfather. You find him. You aim your weapon, but you slip on a banana peel. Your shot goes wide and hits a tree. Your grandfather, startled, turns and sees the woman who will become your grandmother, who came to investigate the noise. Your attempt to prevent them from meeting is the very event that causes them to meet. You were always part of that history. You don't have the free will to create a paradox. Then there's the many worlds interpretation which comes from quantum mechanics. This theory suggests that every time a quantum event happens, the universe splits. Every possible outcome occurs, each in its own separate, parallel universe. In this view,
when you travel back in time and kill your grandfather, you don't erase your own existence. You simply create a new timeline, a new branch of the multiverse. In that universe, you will never be born. But you, the time traveler, came from the original timeline where you were born. You can't go home again, because your home is now in a different universe. You've just created an alternate reality and become a temporal orphan. Finally, there's the strangest paradox of them all, the bootstrap paradox, or causal loop. Imagine a history professor who is a huge fan of Shakespeare. A time traveler from the future appears and gives the professor a book containing all of Shakespeare's lost plays. The professor is ecstatic. He publishes them, and they become legendary. Centuries later, in the future, a student copies those published plays into a book, gets in a time machine, and travels back to give them to his favorite history professor. So, who wrote the plays? They weren't written by Shakespeare. They weren't written by the professor. They weren't written by the student. They just exist. They are an object or piece of information, with no origin, trapped in an eternal loop of time. These paradoxes might just be philosophical games, or they might be deep warnings from the fabric of reality itself telling us that some doors are not meant to be opened. Whether we will ever conquer time in this way remains a profound unknown. But our relationship with time is already changing at a blinding pace, not because of exotic physics, but because of the technology we are building right now. The future of time might not be about traveling through it, but about reshaping our experience of it entirely. We may not have DeLoreans or TARDISes, but make no mistake, we are already a species of time travelers. Our technology is fundamentally altering our relationship with time, in ways both subtle and profound. Let's start with the device that's probably within arm's reach of you right now, your smartphone. This small rectangle of glass and metal is a pocket-sized time distorter. It annihilates distance, which is a form of time. You can have a real-time conversation with someone on the other side of the planet, collapsing what would have been a months-long journey into an instant. It's also a memory machine. Your photo gallery is a vast archive of your personal past, accessible at any moment. You can relive a vacation from 5 years ago with perfect clarity. This externalization of memory changes how we remember and how we perceive the past. But it also fractures our present. The constant stream of notifications, emails, and updates pulls our attention in a dozen different directions at once. It can make it harder to sink into deep time, that state of focused concentration where hours fly by. We live in an eternal, shallow now, constantly interrupted. Beyond our personal devices, artificial intelligence is becoming the ultimate time management tool. AI algorithms now schedule our meetings, optimize our travel routes, and manage complex global supply chains. They are designed to squeeze every drop of efficiency out of every second. In the future, AI might become a personalized time coach. Imagine an AI that monitors your biometric data, your heart rate, your brain waves, your hormone levels. It could learn your personal rhythm and tell you the optimal time to work, to exercise, to learn a new skill, or to rest. It could help us master our own subjective experience of time, to make every hour count. These paradoxes might just be philosophical games, or they might be deep warnings from the fabric of reality itself telling us that some doors are not meant to be opened. Whether we will ever conquer time in this way remains a profound unknown. But our relationship with time is already changing at a blinding pace, not because of exotic physics, but because of the technology we are building right now. The future of time might not be about traveling through it, but about reshaping our experience of it entirely. We may not have DeLoreans or TARDISes, but make no mistake, we are already a species of time travelers. Our technology is fundamentally altering our relationship with time, in ways both subtle and profound. Let's start with the device that's probably within arm's reach of you right now, your smartphone. This small rectangle of glass and metal is a pocket-sized time distorter. It annihilates distance, which is a form of time. You can have a real-time conversation with someone on the other side of the planet, collapsing what would have been a months-long journey into an instant. It's also a memory machine. Your photo gallery is a vast archive of your personal past, accessible at any moment. You can relive a vacation from 5 years ago with perfect clarity. This externalization of memory changes how we remember and how we perceive the past. But it also fractures our present. The constant stream of notifications, emails, and updates pulls our attention in a dozen different directions at once. It can make it harder to sink into deep time, that state of focused concentration where hours fly by. We live in an eternal, shallow now, constantly interrupted. Beyond our personal devices, artificial intelligence is becoming the ultimate time management tool. AI algorithms now schedule our meetings, optimize our travel routes, and manage complex global supply chains. They are designed to squeeze every drop of efficiency out of every second. In the future, AI might become a personalized time coach. Imagine an AI that monitors your biometric data, your heart rate, your brain waves, your hormone levels. It could learn your personal rhythm and tell you the optimal time to work, to exercise, to learn a new skill, or to rest. It could help us master our own subjective experience of time, to make every hour count. But the most ambitious frontier in our quest to conquer time isn't about management. It's about biology. It's about tackling the most personal arrow of time: aging. For all of human history, aging has been seen as an inevitable fact of life. But what if it isn't? What if aging is not a metaphysical concept, but a biological process? A process driven by accumulated damage to our cells and our DNA. And if it's a process, maybe it can be slowed down, stopped, or even reversed. Scientists around the world are now studying the mechanisms of aging with incredible intensity. They are researching things like telomeres, the protective caps on our chromosomes that shorten as we age. They are developing senolytic drugs that can clear out old, malfunctioning zombie cells that contribute to age-related diseases. They are experimenting with gene therapies and regenerative medicine. This isn't about finding an immortality pill. It's about extending our health span, the number of years we live in good health, free from chronic disease. Imagine a future where a 90-year-old has the physical and cognitive health of a 50-year-old today. What would that do to our concept of a lifetime? How would it change our approach to careers, education, and relationships? It would be a fundamental re-engineering of the human experience of time. And finally, as our understanding of physics deepens, we continue our search for that elusive theory of everything. If we can unite relativity and quantum mechanics, we might finally get a definitive answer on the nature of time. This could lead to technologies we can barely conceive of. Could we manipulate the curvature of spacetime on a microscopic level? Could we find a way to stabilize a wormhole? The answers lie hidden in the final theory of reality. This leads to one last, speculative, and deeply unsettling idea about the future of time: the simulation hypothesis. Some philosophers and physicists, like Oxford's Nick Bostrom, have argued that it is statistically likely that we are living inside a sophisticated computer simulation created by a more advanced civilization. If this were true, then time itself wouldn't be a fundamental feature of reality. It would be the clock speed of the cosmic computer running our simulation. The flow of time would be the processing of code, frame by frame. The laws of physics would be the rules of the program, and a glitch in the code could explain paranormal events or moments of déjà vu. Perhaps the ultimate time machine wouldn't be a machine at all, but a cheat code. The ability to access the simulation's source code and rewrite it. It's a wild, untestable idea. But it's a powerful reminder that our understanding of reality is still in its infancy.
So where does this leave us? We are a species caught between our subjective emotional experience of time and the bizarre, counterintuitive reality described by science. We are trying to manage it, to extend it, to understand it, and maybe, one day, to escape it. Our journey is almost at an end. We've traveled from the dawn of consciousness to the far reaches of theoretical physics, and we are left with the same question we started with. But now it carries the weight of all this knowledge. What is time, really? The unanswered question. We began with a simple tick of a clock, and we found a universe of astonishing complexity. We discovered that time is not a steady, universal river. It is a raging torrent near a black hole, and a gentle stream for an object standing still. It stretches, and it shrinks. We learned that the feeling of time flowing is a grand performance staged by our own brains, a story told with the ink of memory and the chemistry of emotion. We learned that time has an arrow, a one-way direction, only because the universe prefers chaos to order, messiness to neatness, a law of probability that dictates our beginning and our end. We journeyed to the quantum realm and found that time might be a ghost, an illusion that emerges from a deeper, static, timeless reality. So, after all this, does time really exist? Perhaps the problem is in the question itself. We ask, what is time, as if it's a single thing we can hold in our hands and examine. But maybe time isn't a noun. Maybe it's a verb, a process. Maybe time is the relationship between things, not a thing in itself. It is the measure of change. And if nothing in the universe ever changed, would time even exist? In the end, the ultimate nature of time may remain a mystery, a puzzle that connects the largest scales of the cosmos with the most intimate workings of our own consciousness. But not knowing the final answer doesn't have to be a source of frustration. It can be a source of wonder. It pushes us to keep exploring, to keep questioning, to keep learning. What we do know is this: we are here, now. This present moment, whether it's the only real thing or just one frame in a cosmic movie, is the only stage on which we can act. It's the only time we have. So, the next time you look at a clock, don't just see the numbers. See the ancient starlight that taught us the seasons. See the ghost of Einstein, reminding you that your reality is not the only one. Hear the echo of increasing entropy, urging you to create pockets of order and beauty in a chaotic world. Feel the intricate clockwork of your own mind, constructing this precious, fleeting feeling we call now. The journey to understand time is, in the end, the journey to understand ourselves. And that is a journey worth every single second. Hey, if you felt even a shred of calm during this weird little cosmic adventure, if the stars chilled you out or my rambling questions knocked you out, honestly, I'd be stoked if you smashed that like button. Maybe hit subscribe, or, I don't know, pass this sleepy corner of the universe to someone else who needs to crash. Time's weird, right? Slippery as soap, probably fake, whatever. But for now, it's just you, me, and this slow, cozy spiral into dreamland. So, yeah. Good night out there, Space Wanderer, wherever or whenever you've landed.